Hi and welcome to Module 1. This is the Overview module. First, let's have a look at the supported node configurations. A cluster can be as small as one single node. Running a single node cluster obviously means that if you lose the node, you will lose access to your data. So in other words, you are not redundant. To be redundant at the node level, you can add a node to the existing cluster to form an HA pair. A node in an HA pair shares the disks with the other node in the same HA pair. If one of the two nodes fails, then the other node can take over the aggregates of the failed node. Now, if you run an HA pair, you will have something which is called the HA interconnect. This HA interconnect is used to mirror the NVRAM between the two nodes, so that if one node fails, the data that was not yet written to disk is also available on the other node. After having taken over the aggregates of the failed node, the data will still be written to disk. Also, with an HA pair, you will have a network which is called the cluster interconnect. The cluster interconnect is used for heartbeat, configuration management, and volume data between the nodes of a cluster. A cluster can be scaled out by adding more HA pairs to the same cluster. Each HA pair will have to be connected to the cluster interconnect, and each HA pair will have its own HA interconnect. Now, depending on the protocols you use, a cluster can have as many as 24 nodes. The maximum number of HA pairs in a SAN environment depends on the controller types you use. Currently, with all flash arrays, you can have a maximum of up to 6 HA pairs, which is 12 nodes. The configuration limits of all sorts can be found at the Hardware Universe, hwu.netapp.com. So, we can have a single node with one or more disk shelves, we can have a single HA pair with one or more disk shelves, or we can have multiple HA pairs. Client data and configuration data in an ONTAP environment is stored in volumes, and volumes are always part of an aggregate. And you could say that an aggregate is a collection of disks. In this picture you see 4 aggregates, 2 root aggregates, 1 per node, and 2 data aggregates, also 1 per node. Aggr 0 node 1 is the root aggregate of node 1, and Aggr 0 node 2 is the root aggregate of node 2. And we see 2 data aggregates. Of course, you can have multiple data aggregates in the cluster, but you can only have 1 root aggregate, or 1 Aggr 0, per node. In the case of a node failure, the surviving node in the HA pair will take over all of the aggregates of the other node by default. You could prevent that when you halt the node manually if you wanted to. So you can specify a parameter that says that you do not want these disk groups or these aggregates to fail over. When the node joins the cluster again, it can automatically or manually get its aggregates back. This is all configurable. There's a very important volume that resides in the root aggregate. This volume is typically named vol0. This volume is the node volume and contains cluster configuration and log files. So every node has a volume named vol0. Another important feature of the ONTAP cluster configuration is storage virtual machines. A cluster will always run storage virtual machines. SVMs are logical representations of one of 4 types. We have the system type, and there's only one of that type in our cluster. This SVM is used to manage the cluster interconnect interfaces. We have the node type. Each node in your cluster is represented as a node SVM. The admin type is the management SVM. You will usually connect to this storage virtual machine if you want to manage your cluster. So the admin type SVM basically represents your cluster. And finally, we have the data type. Depending on the number of nodes and the protocols used, you can have up to a maximum of 1000 SVMs. This type of SVM is used to present data to our NAS and SAN clients. Data storage virtual machines are the SVMs that service the data. The data of the SVM is stored in volumes, and all of the volumes that belong to a particular data SVM are part of the namespace of that particular SVM. So every storage virtual machine has its own namespace. So in short, the namespace of an SVM contains all of its data volumes. A data SVM will always have one and exactly one root volume. This is a very small volume of 1 gigabyte that is commonly used to mount the data volumes to. These mount points are called junction paths. In a NAS environment, the volumes will have to be mounted, otherwise they will not be accessible by clients. This root volume of a storage virtual machine should never contain data. The only thing you will find in the storage virtual machine's root volume are the junction paths of the mounted data volumes. Now let's have a look at cluster configuration. The configuration of your cluster is stored in something which we call the replicated databases. These replicated databases are, in fact, they're ASCII files, but they are in sync in the entire cluster. They're stored in vol0, and vol0 is the root volume of the node. If you have 4 nodes in your cluster, you will have 4 vol0s. So every node will have one and exactly one vol0. These databases should always be in sync in the cluster. So this means that all nodes will have the same information in their vol0 where it concerns the replicated databases. And this concerns stuff like volumes, IP addresses, aggregates, and aggregate information, and what have you. So it's important to know as well that the root volume, or vol0, is mounted to the /mroot directory on the node. You should not confuse vol0 with the root volumes of data storage virtual machines. Now, before we have a look at the command line, let's have a look at what these RDBs really are. There's 5 of them, and they all contain configuration information. The VLDB contains meta information about volumes and aggregates. bcomd, or the block configuration and operations management daemon, has the SAN information, think of iGroups and such. Viv Manager is for logical interfaces and networking. CRS, or the configuration replication service, is for replicating storage virtual machine config to other clusters. And so think of SVMDR, things like that. And management is for all the things that are not stored in one of the previous 4. So you could think of users, policies, etc. And the location is listed here. We will definitely go and have a look at that later on in another module. So let's have a quick look at what we just discussed. First, I'm going to log into my cluster, which is via 192.168.4.100, and I'm going to log in as admin. After I've logged in, I'm going to list my nodes. So I run cluster show, and it tells me that I've got 4 nodes in my cluster. Because they're simulators, we can't say that we've got 2 HA pairs. Unfortunately, the simulators are in a non-shared disk environment, so each node has its own disks. In real life, this 4-node cluster would consist of 2 HA pairs. Now let's check the storage virtual machines. We run vserver show, and we see that we've got 7 SVMs, 4 node SVMs, 1 admin SVM, and 2 data SVMs. Now if we go to the advanced mode and run the same command again, we see yet another SVM. This is of the type system. So this is the SVM that is responsible for the cluster interconnect interfaces. So we will have a look at these cluster interconnects and the other network interfaces after we did the networking overview. To see all the volumes, we run volume show, and we see that each node has its own vol0. Also, each vol0 has its own aggregate in which it lives, and the data volumes are in data aggregates, obviously. We have one node 1 agar1, and we've got one node 2 agar1. Both storage virtual machines have one root volume and one data volume each. So we exit and we will continue with networking. Networking obviously is a very important item in the cluster configuration. First of all, if you run 1 or more HA pairs, there is this cluster interconnect. This can either be switchless if you've got 1 HA pair, or it can be switched if you have more than 1 HA pair. You can also use a switch if you've got 1 HA pair, so that's up to you. Each node will have a minimum of 2 10 gigabit interfaces, and both interfaces will be hosting an IP address and connected to the cluster interconnect network. These ports are configured during the cluster initialization or when a node joins the cluster. If needed, you can add more interfaces to the cluster interconnect network to grow the bandwidth, for example. Next to the cluster interconnect, we have a single LIF that is configured for the cluster management SVM. This LIF is a LIF that's always available in the cluster. If the node that hosts the LIF fails, then that LIF will fail over to another node in the cluster. It's best practice to connect to that particular LIF when managing the cluster. In my example just a second ago, I connected to 100, and that 100 IP address was my cluster management interface. Every node in the cluster has a node management LIF. Instead of connecting to the cluster management LIF, you could connect to the node management LIF and manage the cluster. You would end up in the same cluster shell and there would be no difference whatsoever. However, if the node management LIF would fail because the node fails, that LIF would not fail over. So NetApp advises you not to manage your cluster via the node management LIFs. The service processor of every node has its own IP address. The service processor can be used to manage the node remotely without losing connection if you, for example, upgrade a node or troubleshoot a node. So you can shut down or reset a node from the service processor and still have connection to your environment. Unfortunately, we have no service processor in the simulator, so we cannot have a lab on that. Finally, of course, we've got the data LIFs to use in the cluster. These can be configured to fail over to other nodes in the case of NAS LIFs. SAN LIFs will not fail over to other nodes. Then we've got IP spaces, which is relatively new, and by default, a multi-node cluster has two IP spaces, the cluster IP space and the default IP space. This cluster IP space holds exactly one broadcast domain, and that broadcast domain will host the cluster interconnect ports. The default IP space can have more than one broadcast domain, and you could have multiple data IP spaces as well. So you could have a number of IP spaces, and each IP space would have one or more broadcast domains. The advantage of having multiple IP spaces would be that you could have customers with identical subnets. So by default, however, you only have the cluster and the default IP space. So if you have no need for duplicate subnets, your cluster can very well function with just the cluster and default IP spaces. A broadcast domain, by the way, is a collection of ports in an IP space, and these ports are grouped together in the broadcast domain. A very important thing to realize is that an SVM is always connected to an IP space. And this is done at creation time. So when you create a storage virtual machine, you can select the IP space to which you want to connect the SVM. And you cannot change that later on. So if you connect an SVM to an IP space that it should not have been connected to, then you will have to delete the storage virtual machine and recreate it. The cluster SVM is the SVM that is set up during cluster configuration. And this SVM is the only one that is connected to the cluster IP space. So the cluster SVM holds the cluster interconnect ports, and they are part of a different IP space. So obviously the cluster IP space. Do not confuse the cluster SVM with the cluster management SVM, okay? I know it's confusing, but we have a closer look at this in a second. So let's have a look at networking in our cluster. When we run netport show for node 1, we see that we have port A up to and including port F. A and B are in the cluster IP space and cluster broadcast domain. The rest of the ports are in the default IP space and broadcast domain. And then we run net-in-show for the cluster SVM, and we want to list the IP space, the address, the home port, and home node. And then we notice that we only use port A and B of every node, and that these ports all belong to the cluster IP space. When we run the same command, now for SVM CL1, we notice all the management lives and we see that they live in the IP space default. When we run net-in-show without vserver or fields, we see all our lives, including the data lives that belong to the data SVMs. And if we run net-in-show and just want to see the IP spaces, then that will tell us that all SVMs are connected to the default IP space except the cluster SVM that hosts the cluster interconnects. And if we list the SVMs to which IP space they are connected, then we see that the only SVM connected to the cluster IP space is the cluster SVM. The last thing that we will have a look at in this overview is the different shells that you should be aware of before we continue with Module 2. So let's have a look at the different shells that NetApp offers. It's very simple. We have 3 different shells. The first one is the cluster shell. This is the shell that you will be in during cluster administration, most of the time. Whatever you do in this shell will reflect in the entire cluster. So the RDBs will be updated when you create a volume or live or user, or when you remove things or modify things. This shell can be accessed connecting to the cluster management live or to any of the node management lives. The second shell is the node shell. This shell will give you access to the node itself, so your commands in that shell will not update the configuration of the cluster. For those of you that have worked with a previous solution of ONTAP, which is server mode, you will be able to run server mode commands. Just keep in mind that what you do in that shell affects the node only. It doesn't affect the cluster. So from the cluster shell you can connect to a node shell of any of the nodes in the cluster. And then there's the system shell. This shell gives you access to Unix. And also very important, this shell only affects the node that you access. So to access the system shell, you will have to unlock the diag user and give that user a password. And logging into the system shell requires diag mode. And you have to log in as the diag user. So let's have a look at that. We log into our cluster, and from the cluster shell we connect to the node shell of node 1. Now when we run vol show, we get an error message because this is not the cluster shell that we're in. We're in the node shell. And in the node shell we should run vol status. And the only volumes that we see are the volumes that are local to this node, to node 1. We do not see any of the other volumes. We don't see vol 0 of any of the other nodes. And we only see one of the SVM root volumes. The other SVM root volume is obviously in a different aggregate on a different node. So to exit this shell, we type Ctrl-D or exit. Now to unlock the diag user, we go to the diag mode first, and then we run security login unlock username diag. And then we give the user a password. And finally, we can log into the system shell by specifying the node we want to log into. And if we want to return to the cluster shell, we type exit to leave the shell. And we're back in the cluster shell. Finally, there's one thing we definitely have to look at in this overview module. We have to be aware of how the data traverses the cluster. When we take a closer look at the node in a cluster, we see that in fact it is made up of some software modules. They used to be called blades, but now they're called modules. But basically this is software. These modules process the data that enters the node. The first modules are the network and SCSI modules. Obviously the network module is responsible for NAS traffic and the SCSI module is responsible for SAN traffic. Then there's the cluster session manager, and this is a very important module because it's responsible for determining where the data should go. This means, is the data to be sent to the data module of this local node, or does it have to be sent to another node in the cluster? The data module is responsible for writing the data to disk. We could say that this last module is part of Waffle. So actually the data module takes care of NVRAM, writes the data to the actual volume, and then flushes NVRAM. In the first scenario, the data enters the node and is destined to be written to a volume that is hosted in an aggregate on that particular node. In the second scenario, the data enters the node and is destined to be written to a volume that is hosted in an aggregate on a different node in the cluster. In the first scenario, the data enters the LIV. Let's say it's NAS data. The network module receives the data and copies it to the cluster session manager. The session manager checks the RDB that deals with volumes, which is the VLDB or volume location database, and that sees that the volume is local to the node. So it copies the data to the data module. The data module stores the data in NVRAM, creates a stripe when it's time to do that, adds parity and writes data to the volume. After the data has been written, NVRAM is flushed. In the second scenario, the data enters the network or SCSI module, is copied to the session manager, and the session manager checks the VLDB. Now, the volume is not local to the node, so the data will be sent to another node via the cluster interconnect. The other node will copy the data to its data module, and the NVRAM and the rest is taken care of by that data module on the other node. Now, I hope this overview module was helpful, or at least not too boring, if you're familiar with all of this already. But just to make sure that we're all at the same level before we start talking about booting your system and doing some troubleshooting. So hope to see you in the next module.